All right, today we are diving deep into the brain. We're going to tackle a huge question, one you've probably thought about yourself. Why does our ability to learn change so much as we get older? Well, it turns out there's this incredible new research uncovering the secret timers that control, well, pretty much everything. I mean, you've seen it, right? A kid picks up a guitar or a new language like it's nothing, just effortless. Meanwhile, we as adults can spend years struggling to get even close to that level of fluency. So, what's really going on there? Well, the answer is way cooler and more complex than just saying, oh, young brains are just better. The real secret, it's all about these hidden biological clocks, timers that open and close these amazing temporary windows for what you could call super learning. Now, in the science world, these windows have a name: critical periods. A critical period is just a specific time when the brain is, well, it's like a sponge. It's uniquely sensitive to certain things from the environment, and it uses that information to rapidly wire itself for a specific skill, whether that's seeing, hearing, or speaking. Okay, so we've got these learning windows. But here's the thing. It's not like one big learning mode that the brain just turns off one day. Nope. It's much smarter than that. Think of it more like a massive construction project with a whole bunch of different, staggered deadlines. And what's so cool is that these critical periods don't all happen at the same time. They're staggered. The brain is super efficient. It doesn't try to learn everything at once. First, it nails the basics, the foundational stuff like seeing and hearing. Then, once it's got those down, it uses them as building blocks to open up later windows for the really complex stuff like language. It's this beautiful step-by-step process. So this all points to a really fundamental trade-off. The young brain, with all these learning windows open, is this incredible machine of flexibility. It's designed to learn, adapt, and be shaped by everything it experiences. But the adult brain, it's playing a different game. It prioritizes stability and speed. It takes all those circuits it built when it was young and optimizes them, making them super fast and reliable, but a lot less open to big changes. Okay, so if these learning windows are timed so perfectly, you have to ask, who's the conductor of this amazing biological orchestra? What's pulling the strings? Well, researchers have zeroed in on one very, very special type of brain cell. Say hello to the Parvalbumin positive neuron, or let's just call it a PV cell. You can think of these guys as the master conductors, the absolute timing hub for brain plasticity. It's their growth and their activity that basically tells a brain circuit, okay, you're open for business, and then later, all right, time to lock in what you've learned. So how do they do it? It's a two-part story. First, as these PV cells mature, and get this, they need input from the outside world to mature properly, they open the learning window. Then, when it's time for that window to close, they get wrapped up in these things called perineuronal nets, or PNNs. These nets are basically molecular brakes. They clamp down, stabilize the circuit, and lock it into its efficient adult state. Right, but what controls the conductor? If PV cells are the orchestra leaders, who writes the music? And this is where things get truly mind-blowing. It's not just one clock. A totally new way of thinking about this suggests the whole system is run by at least 4 different clocks, all ticking on completely different timescales. This image here is basically our roadmap for the rest of this journey. It shows us that plasticity isn't just some simple on-off switch from childhood. It's influenced by everything from brain waves firing in milliseconds to our daily rhythms, all the way to things passed down across generations. It's a lot, so let's break it down one clock at a time. First, let's look at the fastest clock of all, the one that works in the here and now, from one moment to the next. We're talking about the millisecond clock, gamma oscillations. These are super high-frequency brain waves. We're talking up to 80 times a second. And guess who's generating them? Our old friends, the PV cells. These waves are like a real-time readout of how ready a circuit is to change. So when a part of the brain is really plastic, you see these gamma waves just surge. Okay, let's zoom out a bit. From milliseconds, now we're looking at the clocks that tick over days and even months, the ones that really shape how we develop. And believe it or not, this connects right back to our daily body clocks. Our circadian rhythms, the stuff that tells us when to sleep and when to wake up. It turns out the very same genes that run that daily clock also control how our PD cells mature. Think about that for a second. The 24-hour rhythm of your body is directly tied to the months-long schedule of your brain's most important learning windows. It's all connected. And now, for the slowest and maybe the most profound clock of them all. This is the one that ticks not just across a lifetime, but potentially across generations. This is the clock of epigenetics. Now, epigenetics is a bit of a tricky concept, but think of it like this. It's a series of chemical marks on top of your DNA. It doesn't change your actual genetic code, it just changes how your body reads that code. And our life experiences, things like stress or our diet, can actually leave these marks. And those marks can set the entire baseline for how plastic your brain is, a baseline that might have been influenced by the lives your parents or even grandparents lived. So how can that even happen? Well, it's a three-step process. Step one, a parent's environment, say a lot of stress or a really enriching life, alters their own biology. Step two, those changes can sometimes leave epigenetic marks on their sperm or egg cells. And step three, the child then inherits those marks, meaning their brain development starts from a slightly different place. It's almost pre-tuned to be more or less plastic. It's this incredible idea where nurture in one generation can literally become nature in the next. So you've got this beautiful system of 4 nested clocks, all working together. It's an exquisitely tuned machine. But what happens when those clocks get out of sync? As you can imagine, the consequences for our health and development can be pretty serious. Researchers are finding more and more links between mistimed critical periods and certain neurodevelopmental conditions. For instance, if the learning windows for seeing and hearing don't line up correctly, the brain can struggle to integrate those senses. That's a challenge sometimes seen in individuals with autism. And it's not just the big developmental clocks. Even messing with the daily circadian clock has been linked to worse outcomes for teenagers at risk for psychosis. It just goes to show how incredibly important this timing really is. So this all begs the question, once these learning windows close, are they slammed shut forever? Well, that is the billion-dollar question, and it's driving some of the most exciting neuroscience happening right now. Amazingly, scientists are actually figuring out ways to try and reopen these windows in adults. They're trying all sorts of things, like chemically dissolving those molecular breaks, the PNNs, on the PV cells, or using drugs that make our DNA more open and readable again. Even things as simple as our really stimulating environment or certain antidepressants seem to have an effect. And the ultimate goal here is to help people, to restore a youthful kind of plasticity, to help the brain recover from injury or even relearn things it has lost. And that just leaves us with this one final, really tantalizing idea. The brain already has all the tools to control its own ability to change. It's got the clocks, the conductors, the brakes, the whole shebang. So as we get better and better at understanding this biological code, you just have to wonder, could we, one day, learn how to become the conductors of our own neural orchestra? Could we choose to reopen our own learning windows whenever we wanted at any stage of our lives?